Here we are looking at the key to the Chapter 4 test. And so question number 1, you should look at that and say, an empirical and molecular formula problem. So in a problem like this, where you are given the percent composition, sometimes you might just be given the mass, but here we're given the percent composition, and we just change that percent to grams, grams to moles, divide by the smallest, and if these had not come out as whole numbers, we would have had to multiply them by some small coefficient to make all of them a whole number. But in this case, we came out with 1.2 grams of potassium, 1.2 grams of carbon, and 2.4 grams of oxygen. And that came real neatly to a 1 to 1 to 2 ratio. We determined that the empirical formula, the lowest whole number ratio, is KCO2. And the order of that is not particularly important, although usually we write metals first in any kind of compound like this. Now the problem went on to say, if its molar mass is 166, what is its molecular formula? Well, here's the solution to that. Now the empirical formula, if you add up a potassium and a carbon and an oxygen, is 83 grams per mole. So the molecular mass, you'll see, is just twice that big. Molecular mass divided by empirical formula mass gives us a coefficient of 2 that we're going to multiply by this formula. So the empirical formula is K2C2O4. Question number 2 is a stoichiometry problem where we're finding the limiting reactant and then finding some other questions about that limiting reactant. So part I, which is the limiting reagent? Well, notice here we've balanced our chemical equation. We have a ratio of 6 waters to 1 aluminum sulfide. So notice here, I've kind of summarized that. We need a ratio of 6 to 1. And we've taken the given mass of each of those reactants and calculated the number of moles. Now there are several ways of doing this problem, but that's one of the ways. And so we're looking here at we have 0.09 moles of aluminum sulfide and 0.55 moles of water. Well, what is that ratio? Well, that's a ratio of 0.55 to 0.09, so a ratio of 5.5. Now you'll notice that in order to bring that to a ratio of 6 to 1, we would need more water. So the amount of water we have is too small. So water is the limiting reactant. So part 2, what is the maximum amount of hydrogen sulfide that could be formed from these two reagents? And so since water is the limiting reactant, that's the thing we're going to use to determine how much of the product can be produced. So you'll notice we're going to start with water. And of course, in our balanced chemical equation, we get 3 moles of hydrogen sulfide produced for every 6 moles of water that we start with. And the molar mass of the hydrogen sulfide is 34.08. So that brings us to, it appears this is 9.45 grams of H2S, hydrogen sulfide. So that is the amount of hydrogen sulfide that can be produced. And in part III, so the question is asking how many grams of excess reagent remained after the reaction is complete. And there are several approaches to this problem. I chose to figure out how much was used. It's used in a ratio of 1 aluminum sulfide for every 6 waters that are reacted. And so the mass of the aluminum sulfide that's actually used, here's the molar mass, and if we multiply that out, we're going to find out how much aluminum sulfide was used. So the amount that was used turns out to be 13.9 grams of aluminum oxide. Aluminum oxide? That should be aluminum sulfide. Not sure why it's written as aluminum oxide. Let's fix that. Aluminum sulfide. So the original amount was 15 grams. We used 13.9, so the remainder is the 1.1. Whew! Too many computer problems there. So in problem number 3, we were going to do 3 things. Write the correct products. Well, here we have 2 ionic compounds that at least we are assuming they are, this reaction will not write if they're not in solution. So even though it appears that this one may not be real soluble, there must be enough of it dissolved to make a solution. So this is going to be aqueous, and this is going to be aqueous by definition. So we're going to write the correct products. Cadmium sulfide would definitely form an insoluble product, and ammonium phosphate would definitely form a soluble product, if indeed we're given that those 2 reactants are actually an aqueous solution. And then we're going to write the symbol to indicate if the product is aqueous or solid or liquid. So ammonium phosphate is soluble in water, so that's going to be aqueous, and cadmium sulfide is not going to be soluble in water, so we're going to call that a solid. And then we're going to balance the reaction, and this reaction is balanced with a 1, a 3, a 3, a 2 should balance the reaction. So this was question 4 on the test. Show how many milliliters of a 1 molar solution of magnesium chloride must be diluted to make 250 milliliters of a 0.3 molar solution. So we're using the dilution equation. Molarity times volume of the first equals molarity times volume of the second. So here we have the molarity and volume that we're going to dilute to. We're going to dilute to 250 milliliters, or 0.25 liters, of a 3 molar solution. And so that means we're going to solve for V1 here. So rearranging the equation, V1 equals 0.3 times 0.250 divided by 1, and that comes to be 0.075 liters, or of course 75 milliliters. In problem number 5, we're supposed to compare the 3 types of reactions: molecular equations, complete ionic equations, and net ionic equation, by writing each type of equation for the reaction of calcium chloride plus silver nitrate. Calcium chloride, have to get the formula right, CaCl2, and silver nitrate, AgNO3. Those are both aqueous. They produce, in a double replacement reaction, silver chloride, which of course precipitates out because it is not soluble in water, and calcium nitrate, which is an aqueous solution. Now that's usually considered the molecular equation. The complete ionic equation shows all the ions separated out. The calcium 2 plus ion, the chloride ions, and there are 2 of them, the silver ions, and there are 2 of them, the nitrate ions, and there are 2 of them. And that produces silver chloride, which, being a solid, is not ionized. It's not floating around separated in the solution. It's forming a solid. It's clumping together and making a precipitate. and that's balanced with a coefficient of 2, and there's calcium with a +2 charge, and 2 nitrates with -1 charges. That's the complete ionic equation. Now, what's the net ionic equation? Well, the net ionic equation is designed to show us just the important things that are going on. And then, of course, keeping in mind that there's some other stuff still floating around out there in solution. But we're interested in the reaction in this particular equation. It is important to remember, though, there's still calcium and nitrate floating around in this solution, because sometimes you have to use that knowledge in your chemistry problem. But right now, to get net ionic equation, just the stuff that reacts, we're going to cross out the things that are identical. In other words, this calcium Ca2+ and this Ca2+ cancel out because they're the same on both sides of the equation. What about the chloride ion? Well, here it's an ion, but here it is not in its ionic form. Can't cancel that. So the other thing that cancels is the nitrate. They cancel because they're both ionized and are identical species. So what's left? The silver and the chloride producing silver chloride. And it is balanced in this form, and that's exactly what the net ionic equation should look like. So there is the answer to number 5 on your test. Number 6 on the test was just like those titrations you had been doing in lab, where the initial reading on the burette of acid was 1.23, and you used acid and the final reading was 37.89. That means you used 36.66 milliliters of acid in this titration. And the base, the sodium hydroxide, you started with 0.2, and you titrated or used up or added 50.98 milliliters down to 50.98, so that's a change of 50.78 milliliters. So these are the volumes you'll be working with in your titration equation. So the molarity of the acid is what we wanted to solve for in this problem, and it's going to equal the volume of the acid that you titrated. That's going to equal the molarity of the base times the volume of the base. And so solving for that, you should end up with 0.109 times 50.78 milliliters divided by 36.66 milliliters. The milliliters cancel, the unit left is molarity, and it should be 0.151. Now let's see if that seems to make sense. Our base had a concentration of 0.109, and it took less of the acid than the base, so it seems reasonable that the acid is a stronger acid, or more, I should say, more concentrated acid than the base.